Hey everyone, just wanted to do a video here of our first lecture video for our environmental geology course. I'm going to try to make this as brief as possible. This PowerPoint, it was made by McGraw-Hill, and I've looked through these. They're pretty handy. What I'm going to do is I'm going to put a file in these for you to review on your own if you would like in each of our lessons. And they're really good just for notes, just kind of a summary of what you're going to read about in your textbook. So it's a good review item for you for your test and things like that. What I'm going to do is these have several slides in them. And because I don't want to sit here and talk for like an hour or anything, I'm just going to kind of run through these and kind of use it as a crutch for me to kind of come up with some ideas and just add a little bit to some of these slides. Some of them I'm just going to run right through. They don't really require any additional discussion or examples or anything. But a few of these things I do want to touch on just a little bit more to make sure that everybody kind of understands the concepts that we're going to be discussing in this course. So when we're talking about environmental geology, and I referenced this in my intro video, and if you haven't watched that, I suggest you do so, just because it's going to kind of outline the course and let you know what I expect of everybody in the course and how the semester is going to go. It's just good background information, so I highly suggest you check that out and make sure you make note of the fact I need you to communicate with me on assignments, any of your needs, any issues that may arise. Be sure to reach out to me and let me know via email. So the Earth, we're going to get right into this, is approximately 4.5 billion years old. What makes us unique is we're the only planet in our solar system with liquid water. The reason that is we're one of the few that has water at all, and second is that we're in a zone called the habitable zone around our star that allows that water to be in liquid form, not just in a gas form, which is water vapor, or frozen, which is ice, obviously, but it's usable to us, and this is our home. This is the only place that we have found other life in our solar system and anywhere else for that matter. Probably a lot of it has to do with our capabilities of looking other places other than our solar system. One thing I do want to point out at this point right now, the second chapter in our book deals with space, the universe, and how we relate to other planets in the solar system. So I have intentionally left that chapter out of our lessons. It is a good chapter. It'll give you some good background information, but with our schedule, especially this compressed schedule that we have in the bi-term, I felt like that was more of an astronomy course than it was a geology course, even though it does give us background information for what we're going to be studying. So if you would like, I'm sure everybody will jump right on this, but if you want to kind of just at least scroll through those pages and just kind of take a look at some of the diagrams and stuff, it might be useful, but you don't have any assignments in that specific chapter. So geology, just a really quick crash course, is basically the study of the Earth and Earth processes. And it's broken down into both physical and historical geology. They go hand in hand. Of course, physical geology is us studying the processes that shape and modify the Earth. So the rocks, the plate tectonics, volcanoes, earthquakes, all that stuff is geology. The historical geology part of it is, okay, we are studying these processes that are ongoing. Have they always been here? And why did these rocks form the way that they did? What is going on now that might have gone on in the past? So those are the two main branches of geology, but they really go hand in hand with each other. And then at the bottom you see environmental geology is basically bringing humans into this equation. Okay, there's two sides to this, and I mentioned this in the intro video. So first of all, how does geology affect us as humans? In other words, are there disasters that happen because of geology that we need to know about? The answer is yes. Of course, we have volcanoes, we have earthquakes. The other part of that, though, the flip side of that is what are we doing as humans that we affect these processes? Do we have an effect? What is that effect? Is it good or bad? That's what environmental geology is, and that's what we're going to be discussing throughout this semester. So, a little background, just real quick. I wanted to touch on this just because this is the basis of all science. And in today's world, it's very important that you kind of understand what science is. We've been bombarded in recent years, and probably within most of you all, it's been your entire lives. But it's relatively recent with regards to technology, as we've had the internet, we've been online, we've got bombarded with all these different sources of information. And now, anybody that has a computer and can click to YouTube thinks they're a scientist and they understand everything from geology to COVID to anything else. And that is just inherently ridiculous to think that somebody's an expert just by doing this. Hopefully you'll understand as you take science courses in school that science is a process. It's not a book of facts. It is an ongoing process to gain more and more knowledge on different types of things. Most of those things are from our natural world. Some of them are from our human world. It runs the gamut. But this process has a certain structure on how it has to be done. You see at the top, you're talking about hypotheses. At the bottom, it talks about theories and laws. Basically, I'm going to break this down for you in very general terms. Essentially, what science is it's observation. You observe things either in the real world or in a experimental phase, like think about a laboratory or something like that. So either it's natural, like geology, a lot of that is natural because we have to look at things that happened a long time ago in things like rocks and earthquakes in the real world. Chemists, on the other hand, can go in a laboratory and they can recreate a lot of things that they're studying. So those observations and experiments can be different types of things with different types of science. Nonetheless, they are concrete observations of what's happening in the real world. So keep that in mind. And then, as these observations are made, scientists create hypotheses. And what that means is they come up, think kind of like an explanation of why something is happening, but it's based on their observations. It's not just made up out of the blue. It's not just something that they thought, well, this fits my narrative, so I think it happened like this. No. Hypotheses are from observations of experimentation or real-world phenomena. And once you get a bunch of different hypotheses together, you start to develop theories. Now, mind you, I see a lot of this online, and you hear a lot of it in arguments. Well, it's just a theory. A theory is pretty solid in its own right. A theory is a group of hypotheses that have been studied, and you can look at the correlations between all of those, and you can say, okay, well, this is probably what's happening. And that's what a theory is. And then a law is pretty much 100%. It's been proven, just 100%. There's pretty much no argument for that. So I kind of look at it as a theory. You're probably about 95% sure. A law is 100% sure. That's the way I kind of look at it. Some people might not like that definition, but that is the way I look at science. So that's why when we see, and this is a good time to talk about this coming out of COVID, and you saw all the different ridiculous ideas and this and that, and it's just a hoax and blah, blah, blah. This stuff is studied a lot by very, very solid scientists. It's not just something that's made up on the fly. I wanted to get that out there and let you know that's what we base all of science on, is that type of study. So the scientific method, You've got this in your textbook. You've got it here. I'm not going to go through this step by step, but again, it kind of just demonstrates what I just told you, the testing and validation, the forming of the hypotheses, etc. So I've already mentioned this, so I'm going to run through this slide. The two categories that we have in environmental geology are hazards. Those are the things that can affect us as humans. And then the resources. Those are things that we have available to us from the earth, but we can also affect in return. Again, examples of these two things that I just mentioned. Resources, we have renewable and non-renewable. And we're going to talk in a few minutes about sustainability. So renewable resources are resources that we can use over and over again. We can recycle those or cycle through those and not lose anything. So they're infinite. Soil and water, they use as an example here. So one thing I want to point out before I get into these specific examples is it's also relative in time scale. So there is a finite amount of water on this planet. Whether it's in the oceans, it's fresh water, it's in the Earth's mantle, whatever, wherever it is, not the mantle, but under the Earth's crust, wherever it is, it's there. And there's an X amount of it. So an argument can be made, well, that's finite. Well, for our purposes as human beings, it's renewable because we have plenty of water available to us on this planet. But how we utilize that water and how that water is conserved and how we pollute or don't pollute that water, that's why it's renewable. We have plenty of it. We can cycle through it. We can use it again, and use it again. And we should be good if we're smart about it. Now, if we're not smart about it, that's when we get into problems. And we're going to study a lot about that in this course. Soil is also a renewable resource, even though it does take some time to build soil. Soil is a combination of things. It comes from rock. There's biological matter in soil. There's a lot of different variables in there. But if we take care of soil, we do have plenty of soil, and we can rehabilitate it if we have ruined it in the past. And we'll also talk about that a lot. Now, non-renewable resources, when you're talking about energy, now this is talking about fossil fuel energy, not renewable energy, like solar, for instance. Solar energy comes from the sun. The sun shines every day. It's always going to be there. If it's not there, we're not here either. We're not going to even worry about it then, of course. But the sun, water is renewable energy, hydroelectric. Mineral and rock. So this is another one we have to talk about time scale. There's an X amount of mineral on this planet. There's so much rock on this planet as well, but rock is forming every day. We have sedimentary processes going on in the oceans that's forming new rock every day. We have volcanic resources on the planet that's forming new rock every day. But to us, in our lifetime, and really the lifetime of humanity in general, it's not renewable because it's not replenishing that much in our biological time scale. So for that reason, they would classify it as non-renewable. That's the same way as our fossil fuels. The oil, gas, coal, all those are non-renewable. Now, at some point in history, they formed through biological processes. You probably all heard stories about how they form swampy areas where stuff settles down and decays over time. All the biological matter decays, gets trapped in rock layers, and then it becomes oil, gas, whatever later on. And that is true. That's how it forms. So you might think, well, if it's formed like that, it's probably forming today somewhere. And you're right, it is. If we have bogs and swamps in certain areas, that decay is happening today. If you come back to Earth in 500 million years, it's been covered up by sandstone. There might be new oil layers. Is that going to benefit us? Absolutely not. It's not renewing on a basis that it's pertinent to our lives or the lives of any generations after us. We're talking millions of years. So it's non-renewable. Another point I want to make on here is we talk about, there's a lot of discussion right now on the oil and gas industry and drilling more. There's a finite amount of this stuff under the Earth's crust. that's been formed. And if you think about how long we've been utilizing oil and gas, all the low-hanging fruit has been tapped. We've already drilled. We hear the politicians, I'll just drill more gas and oil and we'll be fine. It's not that simple. The news cycle politicians, they like to talk about things kind of to get votes and not necessarily in a intelligent or a real world scenario. The longer we go in time, we're seeing less and less oil and gas and coal reserves. The longer we go in time as well, we're having to travel further to get those. In other words, we've drilled all the easy stuff. Now we're on stuff that might be harder to get to. So far away, it's going to cost a lot of money to transfer it to a place that we can refine it, and the quality of it is very poor. I'll give you an example. In Canada, we have the tar sands, or the oil sands. They call them both things. That's layers of sandstone that has a high content of oil, and the tar is just thicker oil, basically. So that's a huge resource. There's a lot of it up there, and a lot of politicians talk about that. Well, we should get that. We should tap that. Great. The problem is first of all, it's terrible quality. It's got the worst stuff in it with regards to pollution. It's dirty, and the consistency of it and the chemical properties of it, it's very difficult to refine. So the other thing is, it's a long way away from any refineries. We have to pipe it or ship it somewhere else to get it refined. So you put all those variables together, and it's expensive. Very expensive to use that. So when we talk about, today, in today's world, the gas prices, that's a big discussion right now. People don't understand that we've already used all the easy stuff, and we're getting to the point now where it's just getting more expensive to do these things. The reason we import so much from Saudi Arabia, because it's cheaper to import from halfway around the world to use the stuff that we have here. And that's the bottom line. Everybody, the politicians and the news cycles, they want you to think differently, but that's what's happening right now in the world. And that's even more of a reason to go to renewable energy, is so that we won't have to be dependent on these other areas any longer for any needs. So geologic time. So we have relative and we have absolute. So relative means the law of superposition. You're going to see that in your textbook. Very simple. The rocks on the top are younger than the rocks on the bottom. The deeper the rock, the older it is. Because generally speaking, rock layers form on top of each other. So the deeper you go, the older the rock layer is. And based on that, they've developed what they call a geologic time scale. So we have ages of different rock layers that we can study and compare and contrast around the world and start to come up with these hypotheses on how they were formed, what environment they were formed in. This particular diagram here shows you a fossil that's found in one rock layer. We use trilobites as a big example of this because they were a very unique animal that lived at very specific times in geologic history. So for instance, if you find a trilobite fossil in a rock layer here in Kentucky and you find that same trilobite fossil in a rock layer in Europe, then you know those two rock layers are about the same age because they have the same animals living in those. Just a little example there. You cover this in your textbook a whole lot. This is actually the geologic time scale. I'm going to include a video from YouTube in your lesson plan. Pretty good to watch that. A lot of times when you see the geologic time scales, so we're talking about geology here, we're talking about rock layers, right? But a lot of them talk about, when you start watching the video, we're talking about the animals and the environment that these rock layers were formed in. So even though we're talking geology, we really like to explain, okay, what was going on in the world at that time that these rock layers were formed. Why were these rock layers formed the way we were? Why do we see these fossils in these rock layers? So that's why you're going to see a lot of that, even though it's kind of biology and ecology, it has a lot to do with these rock layers that were formed. And then you see the absolute dating of rocks. You've got the rock layers, and the superposition is kind of, it's kind of a comparison of when they were formed. But absolute, we can use radioactive decay of certain elements in those rocks, and we can determine how old they are. So those are the two types of dating of rocks. This slide, I always find these kind of interesting. Sometimes they're more in a more visually pleasing kind of chart or timeline. But this gives you a general idea. So the column on the right, that's 1 year. So we know what a year is, right? So we know how long a year is. And the column on the left is giving a comparison and how long ago or how long that took within a year, all these events that you see. And if you look at the very bottom, this is just giving you a comparison in where we are in our geologic time scale. Basically, for probably most of your lifetimes, you've been alive less than around 1/10 of a second in geologic time on a yearly time scale. So almost nothing. 4.5 billion years is a very, very long time. And you see at the top, it took, if you're comparing this to a year, it took a month and a half before you even seen any rocks on this planet. So just look that over, take a look at it. Like I said, it's always kind of interesting. The one thing I do want to point out, the first modern human fossils, this is fossils from when we probably didn't even look like we look now. Still look more like a primitive primate at that time. However, that's only 23 minutes before midnight at the end of the year. So a very, very, very short amount of time in geologic history have humans even been around, much less modern humans in development. That's why when we talk about all these environmental issues that we talk about today, and people sound alarmed about these, that's because we've been around this crazy short amount of time, but we're seeing that we're changing this earth so quickly, and the environment, the climate, everything is changing ridiculously more fast than it ever happened over geologic time before. I'm going to skip over this. You have this in your textbook. I'm kind of going to go over that. So we're looking at 4 major systems that were all interlinked, but I just want you to be familiar with these names of these categories. So the geosphere is a lot of what we're going to be studying this semester, along with the other 3, but the geosphere is going to be your solid earth, okay? That's going to be your land, your rocks, your minerals, and all that. That's the geosphere. Your hydrosphere is going to be water. You got the oceans, you got fresh water, you got ice. We're going to talk about all that as well. The atmosphere, obviously, is the air and the atmosphere around the earth. And then we have the biosphere, which is all life on earth. That's the biology of earth, the life that exists, which we are a part of that biosphere. So, again, I'm just kind of looking at this. So, population growth. This is another tremendous, tremendous factor that does not get talked about enough in everyday discussions on even the climate or environmental change or stuff like that. And that's because it's very uncomfortable to talk about. Because what are you going to do about this? Bottom line is we have a lot of people on this planet. If you look at something, say a deer population, and I use that because that's close to home, and it's something that Fish and Wildlife, they kind of control that. There's a certain capacity of plants and food that are healthy for a healthy deer population. If you get too many deer, all of a sudden they start to get smaller in size, they're unhealthy, because there's not enough resources to go around for all those deer to eat. That's called sustainability. That's the ability for an organism to live within its environment. So right now we're in the middle of a population explosion in this world. It's more than doubled in my lifetime. That's significant because the earth has a certain sustainability for humans. We can only grow so much food. We can only use so much water before we're going to start really straining those resources. The one thing that's the variable is technology. So as we go forward in time, we're changing our technology so that we can support more and more people. So it's a race of technology versus nature. Are we going to be able to sustain this population growth and survive? If we were living like people lived 200 years ago, there's no way this earth could sustain the population that we currently have. We would have major, major issues. However, technology has allowed us to have more people living within this environment. When you look at these charts and graphs, I want you to just take away what they're trying to tell you. Okay? So exponential linear growth is just a straight line. So that would be X amount of people or X percentage growth of people each year. Exponential means it's not a set percentage. Like it's not just doubling, it's exponential. It's growing several times the factor of the original population every year. And that's not good. This chart, it's kind of hard to see this because the line's so close to the boundaries. But you see the population just steadily increased up. You see the year zero. So you've got year zero. About 1000 AD is right here. And now we're at around 2000 AD. And you can see that you had a flat line for thousands of years. Starts to tick up here, but when we get up closer to 2000, it goes straight up off the page. That is directly linked to that technology I was just telling you about. So in nature, sometimes you see these memes online, nature's trying to kill you all the time. And that sounds harsh, but there are obstacles in nature that kind of control populations of animals. That's kind of true. And we're overcoming those things right now with technology. In specifically, the two things that really have increased is food production and medical technology. Those are the two biggest things that have really, really bumped up our ability to live longer and have a lot more people. Again, this is in your textbook. So these two charts are kind of interesting. I'll show you, this is just a general line, the carrying capacity or the sustainability of an environment. As it goes up, the population can also go up and be okay. But if you look over here, the blue line is the carrying capacity, okay? So it goes this way and then it goes down. And the reason for that is the population has exploded like we are now. And at this point right here where they cross, it's exceeded its carrying capacity. Okay? So at that point right there, that's the inflection point. That's the problem. So as we exceed that, our population, there's a lag time. So the population is going to continue to explode for a while, but the resources have started to go down now. So if they could draw another line right to the top of this curve right here, at this point, we're starting to collapse. And once we start to collapse because we don't have the resources, it's going to be a sharp collapse. And at some point, we're going to have to fall back below that carrying capacity line. Very good graph there. And again, I've said this term several times. Sustainability means that we live within the Earth's capacity to provide resources for future generations. And all of the natural systems on Earth operate this way. That's what I reference the deer population in our area. This is another graph. A lot of lines on here. I know that you're thinking, wow, that's kind of confusing. But if you just break them down, you can see the resources is the blue line. And since 2000, it's on a downward slope. And it's going to continue on a downward slope because, like I said, we're using a lot of our non-renewable resources right now, and they're going to continue to go down. The black line's pollution. You see it starts to go up. Right here, we're 2000, by the way. We're right here, so we're right on this line right here. You see the industrial output has gone sharply up in the last 100 years. You can see they project it to start to go back down. the population is going to peak, and that's population growth, by the way. That's not total population. It's going to start to go back down. The food's going to start to go back down because we're going to start taxing our resources. So our ecological footprint, this is just how many, it's hectares on here, and it tells you that's like our acre, but it's a little bit, it's almost the same size. It's close. So this is a big thing for us to understand. You can see here the comparisons on how many hectares of land. That means general resources it takes for somebody from China to live, from Great Britain to live, for somebody from here to live. So China is half of what we are, less than half, because they don't use as much resources per person. They have a simpler life. As Americans, we waste a lot, we use a lot, we expect a lot. Therefore, our output of pollution and everything else is much greater than the rest of the world. We're kind of spoiled, to be honest with you. We have a lifestyle that's very, very wasteful in this country. Again, this is a projected growth of population. You can see less developed and more developed countries. So the more developed countries probably aren't going to grow a whole lot, but the less developed countries are going to grow extensively over the coming generations. This is in your textbook. I don't want to go over that right now. This is just a population density map, and you can see, depending on where you want to look, the darker the color, the more people live per acre or per hectare. You can see India and China here are just ridiculously populated in those areas, those parts of their countries. All of India, a good part of China. Japan is heavily populated. You know, it's a small country on the islands. It's very densely populated. If you want to see in the United States, you can see the eastern United States is a lot more densely populated than the western part. Just kind of shows you, and if you were to put a map overlaying this on where the resources are the best, you're going to see the same areas because people are going to tend to live where there are better resources. I'm going to skip over this. Easter Island, this is in your textbook. I'll just let you know I would read up on this and learn about this because you're probably going to see this again. It's basically a case study on a population that collapsed because they were in a confined area on an island and their environment collapsed, therefore their population collapsed. Similar to what we're just talking about. This is the history of the the environmental movement started in the 1960s and the 70s. We might talk about it a little more. I'm not as interested in that right now. And that's pretty much it for this lecture. So I'm going to post this online for you to go through on your own. If you keep going in this, in the file, there's actually some alternative slides that have more text on them if you want to read those. A good study aid if you want to see those. But again, this semester, hopefully we have a good time. I hope you learned something. And please communicate with me if you have issues, if you have problems, if you need help. Let me know because since it's an online course, I can't see you. Sometimes I don't know if there's a problem technically with the website or something. So please reach out to me if there are any issues and let me know. So thank you, and I will be back for the next assignment.